All right, guys. So in today's rapid review video, we're going to be going over IMFs again, but the focus is going to be on ion-ion interactions and ion-dipole interactions. So we're talking about, basically ionic bonds. So the strength of the ionic bonds between a cation and an anion. And then remember, when salts dissolve in water, or any polar solvent that has a negative dipole and a positive dipole, but usually water is our go-to with this. The ions separate, they dissociate, and they make two different types of ion-dipole interactions. The cation will interact with the oxygen side of the water for an ion dipole, and then the anion, the negatively charged ion, will interact with the hydrogen side of the water molecule. So again, ion-ion is really just another way to say ionic bond. Okay, so here's a cation, here's an anion. That interaction, you can call it an ionic bond, or you can call it an ion-ion interaction, same thing. Okay, and then again, like if I took one formula unit of sodium chloride and I dissolved it in water, the sodium and the chloride would separate, and then you would end up with ion-dipole interactions like here, and ion-dipole interactions like in here. Okay, now remember, the strengths of these interactions are strictly based on Coulomb's law. So you're looking for a smaller radius for ion, because a smaller ion radius means the ions can get closer to the other ion, or they can get closer to the dipole of the covalent solvent they're dissolved in. Okay, so you're looking for shorter distance between opposite charges. That strengthens the attraction. And then the higher the magnitude of charge. So you could have a +1 ion interacting with a negative the negative side of water, the oxygen side, but a +2 ion would have a stronger interaction. So you want to look at size. The smaller, the stronger, and the higher the charge, the higher the overall magnitude of charge, the stronger the attraction, Coulomb's law. Okay. Just remember, when you're talking about ionic compounds, never bring up electronegativity difference. Electronegativity difference is usually just for when you're talking about maybe different polar compounds. One's more polar than the other because there's a bigger electronegativity difference. Or you could talk about it in terms of different dipole-dipole interactions, but not ion-dipole interactions. So why is this dipole-dipole interaction stronger than that dipole-dipole interaction? That's because maybe that molecule is more polar than the other molecule because there's a bigger difference in electronegativity. So electronegativity is strictly only for covalent compounds, and polarity, not ions. Okay, so just be careful with that. All right, so let's just look at some multiple choice questions. So here we have a chart of ions, and they want us to rank them in order from strongest interaction to weakest interaction with water. So we're looking at the strongest ion dipole moments, and they all have +2 charges. So they all have the same magnitude of charge, but they have different radii. So the zinc is the smallest one, so that would be the strongest interaction, and barium is the biggest one, so it would be the weakest interaction. So let's see. Okay, so the zinc ion dipole interaction would be stronger than the calcium ion dipole interaction, and stronger than the barium ion dipole interaction. Over here, I just made a note. The video is not really covering this, but remember, the higher the vapor pressure, the weaker the IMF. So this would have the weakest IMFs because it has the highest vapor pressure. All right. So again, we have some ions, and this gives us the boiling point of sodium fluoride and magnesium oxide, and they're asking us predict sodium chloride's boiling point. Is it going to be less than sodium fluoride? Is it going to be greater than magnesium oxide? Or is it going to be in between? So it's asking which of these ionic compounds is the strongest, has the strongest ion dipole interaction. Now they give us the radius, but we could just use trend based on this. So we should understand that chloride is smaller than fluoride. So sodium and fluoride are going to get closer to each other than sodium and chloride. So we would expect the sodium chloride to have the weakest ion-ion interaction, and so it would have the lowest boiling point, it would have the lower melting point, it would have the weakest lattice energy. So we should expect sodium chloride to be weaker than sodium fluoride, and also magnesium oxide. Okay. Here we have just this is asking for For which of the following pairs of ions is the energy required to separate the ions the largest? So the largest lattice energy. Remember, lattice energy you can kind of equate towards melting point or boiling point of an ionic compound. It's really the amount of energy to completely vaporize and separate the ions from each other. But it really just comes down to how strong the ionic bond is. So the ion-ion interaction. So since magnesium and oxide are both 2 plus and 2 minus higher charge, and also magnesium is the smallest of these cations based on trend. Now oxide is not the smallest anion, but it is similar in size to, or it actually is the smaller anion. It is smaller than chloride and bromide. So smaller ions and higher charge. So the next couple, all right, so here, this one's looking for the weakest, so we would look for the largest radius, but also the lowest charge. Now, it doesn't have to be the largest one, okay? The sodium and the calcium are very close to each other. So what's going to be the tiebreaker? The fact that sodium is a +1 and calcium is a +2. So sodium is one of the bigger ions, and it has the lower overall charge, so we would expect it to have the weaker interaction, okay? Notice here, we do have an electronegativity chart, but it's strictly talking about covalent compounds and their polarity. So that's when you bring in electronegativity. Don't bring it in when you're talking about ions. Okay. So again, weakest, you're looking for the larger ions with the lower charge. Okay. All right. In the free response, you'll have to draw the ion-dipole interactions, or at least show how the water molecule will surround an ion. And so you just have to remember the smaller hydrogens are the positive dipole of water. So they would face the negative anion, and the oxygen would face away from the negative anion because the oxygen is the negative pole for water. So if you were to draw the water, you would just draw the water surrounding the ion this way. You didn't have to draw the ion dipole, but that's kind of an illustration of the ion dipole there. Okay. Here it's saying 1 formula unit of lithium chloride dissolved in water, and then show the water molecules around it. So you're looking for something like this. You'd have to know that the lithium is the smaller ion in this structure, and that the chloride is the larger structure in this larger ion. So you know that the big circle represents chlorine, and the small circle over here represents lithium. So the oxygen of the water should face the lithium, and the hydrogen of the water should face the chloride, and the ions need to be separated from each other. If you wanted to put a little positive and a negative sign in there to remind yourself, that's fine, but that's really all you had to draw there. Okay. So again, those are ion-dipole interactions and ion-ion interactions, not to be confused with any of the other IMS for strictly covalent compounds like hydrogen bonding, dipole-dipole, and London dispersion. Okay, so just be prepared to talk about both, and maybe even having questions that compare the two. But just remember, electronegativity is not for ions, it's for covalent compounds, and really judging the polarity, how polar it is. Okay, so, all right, do the assessment, and look forward to the next rapid review video.